In this set of notes, we're going to look at some more common discrete random variables. The first one that we're going to look at is what is known as the negative binomial random variable. It's very similar to the geometric distribution that we saw in the previous sets of notes. The difference is, with the geometric, we were looking for the first success, whereas with the negative binomial, we're looking for the rth success. We still need to have independent identical trials. Each trial should result in a success or a failure, and then the probability of success needs to be constant for each of the trials. So here is the negative binomial distribution, and it's a similar format to the geometric, but there are some changes. So as usual, let's diagram the equation into three different pieces. All right, thinking of this first piece here. What we're saying is this is where we're choosing to place r minus 1 successes in y minus 1 trials. So why would we want that? So remember that the negative binomial, what it does is it tells us how many trials we have until we have our rth success. So one way to think of this is we have trial, trial, trial. We keep on going, and so there are going to be y trials, and we know that the last one is the rth success. So we know that in the first y minus 1 trials, that somewhere in there are r minus 1 successes. The next piece of the formula, p to the r, this is where we have r successes, and each of those occur with probability p. And then if we have r successes out of our y trials, we have to have y minus r failures. And again, remembering that q is equal to 1 minus p, so q is the probability of a failure. As usual, we can define the mean and the variance. So here are the mean and the variance for the negative binomial. And you'll notice that this mean and variance look very similar to what you saw with the geometric. So for example, here looking at the mean, before for the geometric we had 1 over p. Well, now since we have r successes instead of 1 success, we have r over p. So let's look at an example. For this example, a representative from the University of Kentucky Football Marketing Division randomly selects people on a random street in Lexington, Kentucky until he finds a person who has attended a home football game in the last 2 years. Let p, the probability that he succeeds in finding such a person, be equal to 0.3, and let x denote the number of people he selects until he finds 4 people who have attended the home game in the last 2 years. So notice this is very similar to the geometric distribution that we saw earlier, except the geometric distribution we keep on going until we find the first person. Here we're going to keep going until we find the 4th. So A asks, what is the probability that x is equal to 5? So what we're saying here is that we spoke with 5 people, and we know that the fifth person that we spoke to was the 4th success. So notice there are 3 other successes that occur somewhere in these 4 trials. So to find this probability, we have the 4 trials circled here, and from them we need to choose 3 where the other 3 successes could be. In total, we're going to have 4 successes, and then that means we're going to have 5 minus 1 failures. Or probably 5 minus 4 failures. And so you can put this in your calculator. And I just realized that I have a mistake here. Let me fix this. I got my probabilities backwards. Our probability of success is 0.3 and our probability of failure is 0.7. So if we place this in our calculator, we'll find the answer is 0.0227. We could also find the mean and the standard deviation. So remember that the mean is equal to r divided by p, which in this case is 4 divided by 0.3. So this tells me on average I'm going to have to speak to a little over 13 people before I find 4 that have attended that home football game. And then we could find the variance as well. And we could use R to calculate negative binomial probabilities, just like the other distributions that we've seen before. So for example, for part A in R, we could place D in binom 5, minus 4, 4, and 0.3. Next, we're going to look at the hypergeometric random variables. So in a hypergeometric, suppose that we have n objects of which r are of one kind and n minus r of a second kind. We draw a sample of n objects without replacement. If y denotes the number of objects in the first kind drawn in the sample, then y is a hypergeometric random variable. We've actually seen an example that follows a hypergeometric distribution earlier. So recall we had the example, suppose that we have 10 blood samples sitting on a shelf. We know that 3 of the blood samples have been contaminated. Draw 2 blood samples without replacement and test to see if they can be contaminated. And we'll let contamination be a success. Alright, so here is just a restatement of the problem in terms of what that would mean in probability notation. But notice this is a hypergeometric. And one way to think of this is we have 2 different types of vials. We have contaminated and not contaminated. Right, so looking here at our hypergeometric distribution, again we can look at the equation to see where the different pieces come from. So looking here at this first term, what this is this is going to choose y from the R type 1 objects. The second term here is going to choose n minus y of the n minus r type 2 objects. And then the bottom accounts for the overall ordering, where we're going to have to choose a total of little n from capital N objects. Alright, so let's see what some examples of this one would look like. So again, we'll start out here with our mean and our variance for the hypergeometric random variable. And so let's look at an example. Suppose that as part of a survey, 7 houses are sampled at random from a street of 40 houses, in which 5 contain families whose family income puts them at below poverty line. So notice we have 2 types of houses, those above and those below. We have 5 that we know are below, so that means we have 35 that are above the poverty line. So what is the probability that none of the 5 families are sampled? So in other words, we're looking for the probability that capital Y is equal to 0, because we're going to let capital Y denote the number of families who are at, who are below the poverty line. So what this says is of those 5 families that are below the poverty line, we're going to choose 0 of them. And of those 35 that are above the poverty line, we're going to choose 5 of them. And then in the denominator, we count for the overall ordering of choosing 5 households from the total of 40. What is the probability that 4 of the families are sampled? Here we can do something very similar. So the probability that capital Y is equal to 4. Of those 5 families below the line, we're going to choose 4 of them. Of the 35 above, we're only going to choose 1 of them. and then again accounting for the overall ordering of choosing 5 households from the 40. What is the probability that at least 3 are sampled? So here we have the probability that y is greater than or equal to 3. Remember that we could instead write this as 1 minus the probability that y is less than or equal to 2. And by doing this, we've got this written in terms of a cumulative probability. So remember, the R functions help us do cumulative probabilities, so that's one way we can do this. We could also do this by hand, but in order to do that, we would need to fill in the formula 3 different times. So the probability y is equal to 0, plus the probability y is equal to 1, plus the probability that y is equal to 2, and again subtracting all of that from 1. If we wanted to find this value in R, we could do the following. 1 minus, and notice we want to find a cumulative probability. Down here at the bottom of the page, we have the different R commands. So we could do 1 minus P hyper 2, 5, 35, and 5, and we would get the same answer there, and it turns out this is equal to 0.0093. Could also find the mean and the standard deviation. So to find the mean, we have mu is equal to the expected value of y, which is equal to n times r over capital N. So here we have 5 times 5 divided by 40, which is equal to 0.625. And for the standard deviation, we could do the following. Alright, so we have one more distribution that we're going to look at, and that is a Poisson distribution. So suppose that we want to find the probability distribution of the number of patients who arrive in an emergency room in 1 hour. And it ends up this is actually related to the binomial. So one way to think of it is we could take 1 hour and we could split it into subintervals that are very, very small, so that the probability that more than one patient arrives in a subinterval is equal to 0. So in other words, you can think of this as being our interval over 1 hour. And what we're saying is that in each of these subintervals, a patient either arrives or they don't. So in each of these intervals, we're going to have a 0 or we'll have a 1. So either one patient arrived or no patients arrived, and we've made those intervals small enough. So the idea here is that we have n trials, and in each of those trials we have, a 0 or a 1, a success or a failure. We can assume they're independent, and so the probability that a patient arrives in one subinterval is equal to p, and the probability that no one arrives in that subinterval is 1 minus p. And here we could let y be equal to the number of subintervals in which patients arrive. In other words, the number of patients who arrive in 1 hour. So what we would have here is a binomial distribution, and we could say that lambda is equal to n minus p, in other words, the average number who arrive within that single hour. And it ends up, you could show that if you take the limit of a binomial probability distribution as n goes to infinity, you end up with this right here. And that is what motivates the Poisson distribution. And so it ends up if n is large and p is small, and the parameter lambda is equal to n minus p is less than 7, you can actually approximate a binomial distribution with the Poisson. And so here y could be equal to the number of events that occur in space, time, volume, or any other dimension, and lambda is the average value of y. So let's look at an example of this one. Suppose that the average number of patients who arrive at an ER between 2 and 3 p.m. is 6. So anytime you're working with one of these problems and you're given the average, what that's telling you is that your rate parameter lambda is equal to that average. So in this case, lambda is equal to 6. So we could say, what is the probability that exactly 5 patients arrive, that should say at the ER, not the bank, between 2 and 3. So here we're going to let y be equal to the number of patients who arrive between 2 and 3. So what we're looking here is the probability that capital Y is equal to 5, which is equal to e to the negative 6, 6 to the 5th over 5 factorial using the distribution on the previous page, and we get the following. What is the probability that at least one patient arrives at the ER between 2 and 3 p.m.? So here we're looking for the probability that y being greater than or equal to 1. We'll notice, again, if we were going to calculate this probability, that would be increasingly difficult because there's no cap. So it could be 1, 2, 3, 4, 5, all the way up to infinity. So the easier way to calculate this would instead be to use the complement, and notice that the lowest value that y can be is 0. So this is equal to 1 minus the probability that y is equal to 0. So again, we could substitute into our formula. And we find the following. So there's a couple more facts and notes here. If we observe a Poisson process and lambda is the mean number of occurrences per unit, then y is equal to the number of occurrences in A units, has a Poisson distribution with mean A lambda. And this result assumes that the number of occurrences is disjoint, units are independent. Alright, so here are our mean and variance, and you'll notice that the mean and the variance for the Poisson distribution are both equal to that rate parameter lambda. And then finally, to end here, we have how you could use R to calculate these Poisson probabilities. And that is going to end this note set.